Hi, I'm Justin Mansell from Active Optical Systems, and this is a tutorial on how to use the AOS Beam Control Scaling Law code and the Control Simulator tool. So you can get these tools by going to the AOS website and going to the bottom here and clicking on the link to the SharePoint site. The AOS website is www.aos-llc.com. If you click on that, it will then take you to the AOS SharePoint. I've already logged in today, so it was a very quick load. If you haven't logged in, it's a much slower load usually. Then you can click on Downloads, Export Controlled, Software, Utilities, and the two tools I'm talking about today are the Beam Control Scaling Law tool and the Control Simulation tool. Okay, so once those are downloaded and installed, and that may require you to uninstall the old versions if you have them on your computer, now you can move on to actually running them. So once I've done that, I can go into, let's start with this one. This is the generic how do you simulate a beam control system tool. So what you can do with this is specify a platform, altitude, so basically height above the ground, target altitude, range, and aperture diameter. Let's say it's 20 centimeter. And wavelength in nanometers. I'll leave it at 1 micron. Actually, a lot of the lasers that I've been seeing lately in the literature are like there. And once you have that, it will then calculate parameters about the engagement. And so these are things like R0, D by R0, the diffraction limited spot diameter on target, and these kinds of things. And so you can take a look at all of these. But what you can do is use this then to assess how much of an AO system and tilt system you need for this to compensate the aberrations. And so you also can specify wind velocities, by the way, I forgot to mention that, and you can specify the wind, the platform velocity, and the target velocity. And those are used to derive Greenwood frequencies and tilt Greenwood frequencies for your system. Okay, so then you can use the simulator tool to take a look at how much of a tilt system you need. So this is a 10 hertz tilt system. Again, this is a 1x HP57, and so with a 10 hertz system, we're not going to get perfect compensation. We're only going to get about 65, let's see, 66% compensation there. Let's see if we can speed that system up into 30 hertz. Good. So this is a 30 hertz system, and now we're getting 80% tilt still compensated. So this is a pretty good system. One of the things I'm not addressing in any of this is what happens when, how do you get this 3 dB bandwidth, and what does that really mean? It's the 3 dB error rejection transfer function, and the next tool to discuss how you can calculate what that is using basic parameters for your system. On the AO side, let me take a look here. We were looking at D by R naughts of 3 for this. Kind of boring, not quite enough there. So let's bring up the HV57 multiplier to about 4x. There we go. Now we're at D by R naughts of about 7, which also affected our requirements for tilt, but let's just leave that one there. And this is estimating with a 5 centimeter R naught in big beam space that I'm going to have about 13 actuators over the full aperture. Not quite enough. I think I'm going to want something more like in the 30s. Let's make this about 2.5 centimeters. Okay, that's good enough. We're in the 50s now. That's okay. And with a 300 hertz bandwidth, we are seeing pretty good compensation here. So this line indicates where you are, and this is the spatial term, and then this is the temporal term. So temporal is a little better than spatial. Let's see if we can actually add some more actuators then. Let me just make it 2 centimeter. There we go. Now they're both crossing over in the 80s, 83-ish% for each of them, 84 I guess for that one. Then when you combine those, you're going to get 70%. So this system with 79 actuators and a 300 hertz 3 dB bandwidth looks like it's going to work well here. I'm going to bring this bandwidth up a little bit. In fact, here, do it till I get somewhere into the 70s, I think would be good. There we go. So 45 hertz there. So this, in order to compensate light propagating from a 20 centimeter aperture, 1 kilometer, 3 meters off the ground, with a HV57 atmosphere and a 4 meter per second wind velocity, 1 micron light would need, to get decent compensation, a 45 hertz tilt bandwidth, 300 hertz AO bandwidth, and that's the 3 dB bandwidth for both of those. And like I said, I'll discuss how you get to the 3 dB bandwidths in a minute with the other simulator tool. And a roughly 2 centimeter or 79 actuator DM, 2 centimeter spacing or 79 actuator DM. Okay, there's another tool built into here that's in its early draft phase, and you can go through and calculate how much of a laser you're going to need for this. This is predicting a 35 watt laser requirement, and there's a lot of parameters to this, including loss per path losses is percent loss per kilometer, target reflectivities, system loss factors, quantum efficiencies, noise electrons, read noise electrons, pixels per spot, whether we're doing Shack-Hartman or whether we're doing tracking kind of things, pulse periods, goal signal to noise ratio, and target sizes. So once those are all specified, you can calculate what you would expect for radiometric requirements for an illuminator. So now we can take a look at the wind velocity. This one happens to be very boring because I said the platform and the target weren't moving, and it's a 4 meter per second crosswind. This is a summary of all the results about the engagement. This is a graphical summary of that, with a summary of all the key parameters like d by r naught, which is on the order of 7. This is the Rytov number, about 0.2. This is the diffraction limited spot angle versus the isoplanatic angle, and that's close to 1, so that's getting pretty bad there. The tilt Greenwood frequency, so this is about how fast a tilt system we would need, and this is in order to start to get good compensation. And then this is the Greenwood frequency. This is about 100 hertz, and you can see we need to be a little bit above those to get significantly improved compensation with this AO system. Okay, there's another piece of this. There's a whole tab on here on conversions. Oftentimes we get units that are funny, and people say, oh, I want to be moving at 23 knots. Well, if you type in 23 knots, it'll tell you that that's really 12 meters a second or 26 miles an hour, that kind of thing. So there's a bunch of conversion things that are in here. You can actually go through and get altitude locations out of the database, but let me go through that and explain how that works. So with this, you can go into Google Maps and start specifying locations. And so I'm going to zoom out. I'm in Albuquerque, New Mexico here. And I'm going to say, let's pretend like we were testing out here in the mountains. You can see that if you zoom out a little bit, you can start to see the contours, but as soon as I zoom in a little, I lose them. So I'm going to just go to satellite mode here. And what you want to do is find a spot. We'll just say this little peak here. Center it up in the screen. Zoom in on it and say, okay, this is my platform location, and say map copy. And it will copy the longitude and latitude for that location. Now I can zoom back out and say I wanted to shoot down here to the front of this hill. Let's say I was doing a fairly short shot here to the front of this hill. Maybe here, it might get me a little bit better. Map copy that as well. Then you click use location. And what it's doing now, as you can see in this progress bar, is it's going off and polling one of the U.S. government databases for altitude along there to try to figure out what the real altitude is for this engagement. This takes a few minutes, and it does require that you have internet access for it. The buttons here allow you to fix some of the common errors that occur when you are using a computer without the necessary details on it. But you can see it came back here, and it's giving me a little snapshot of my platform and my target location, and it's showing me the altitude, the actual altitude, and then the relative altitude along there. And so you can see it's a rapid drop off. Got a little bump here, and that's probably this hill here maybe. And then we get closer and closer to the ground as we approach the target. Okay, so with this, I can go and take a look at what an engagement in a real kind of environment might be. You can see here that now the CN squared plot is mimicking that altitude behavior, and that makes sense. But you can see what happened here. The R naught value dropped let's see, the R0 value increased a little bit, and now my D by R0 is more like 6.19. In fact, let's go back to this graphical summary, 6.2. Okay. So now, because I'm using real locations, it's not as bad. It also filled in for me the ground range. Now, the ground range got significantly longer. I was at 1 kilometer before, and when I picked this range, now we're at 1.6 kilometers. But even getting with this increase in length, I had a decrease in R0, and this had to do with the fact that I'm shooting much higher off of the Earth floor than I was in the previous one. Now, this does take into account the curvature of the Earth, and in fact, it'll plot up for you the curvature of the Earth below here. But it does not necessarily limit your ability to shoot if you're not using a real engagement. Okay, so here we go. I've got the map coordinates. I've got a plot of the altitude, and with that, I can actually start predicting what kind of an AO system I'd need in a real engagement. I think that's basically it for this tool. This tool allows you to do some real quick calculations as to how much of an AO system you would need in order to do a certain job. And the only thing I didn't cover was how I got to these 3 dB bandwidths for adaptive optics and for tilt. So there's another tool we have that can help cover this. Actually, there's one more thing I should say here, and that is that there's a Save Results button and a Save button. Save here allows you to save out to your desktop, or wherever actually, an XML file that you can load back up. Save Results allows you to save all of the results files out. So let me do that real quick. Hold on. Okay, so I've saved a results file out to my desktop. Let's take a look at it. So it not just saves out the results file, but it also saves out a whole bunch of images and things like this. It basically goes through the program and saves out all the images that are available and that kind of thing. This is a plot of the AO results. This is the plot of that wind velocity. This is the summary that I was showing you that shows you the summary of the engagement parameters. Let's see. And it just saves out a bunch of these AOS picture boxes as well. But a lot of these are very good plots for putting into presentations. So you can save those, all those out. And I can open this up. And you can see here, this is just a big XML file of all of the various parameters for the system that could be loaded back into the system with a load operation in order to get back to the same settings you had before. Okay, so that's how the beam control scaling law system works. Now we can talk a little bit about another piece of this. In fact, we can delete all of these old files. Oops. Let's do that. And delete. Good. And now we can talk about this control simulation software. So once that's installed, you can open it up. And what it's doing is trying to take some engineering parameters and determine what bandwidths for the system might be. So it's a real simple tool. Excuse me, a real simple tool. You can specify a sample rate, a latency, and a gain, and quickly calculate what the error rejection transfer function and closed loop transfer function would look like. It's important for this tool to be running it as an administrator. If not, you're going to get a couple of bugs saying, hey, I can't save out the data for this. So let me take a second to fix that. Okay, so I ran this as administrator, and now I can save this out. You can see that with these specifications, I've got a very small overshoot, meaning that I'm probably nowhere near the optimal gain on this. So I can go in here, let's just, because it's a nice round number, work with a 1 kilohertz rate here. Let's bring this latency down significantly now to, say, 1,000 microseconds or 1 millisecond. Yeah, let's bring this guy back up to, say, 0.6. All right, so I'm leaving auto range on this, but you can turn that off and specify the frequency ranges you want to scan over. You can see here that I've got a 3 dB. In fact, I'm going to do a high resolution version. And let's change this to, let's do 300 points. All right. So what it's doing actually is a temporal simulation and reporting the results from the temporal simulation in the background. It does take a little, it's more computationally intensive than frequency approach, but it can be a little more accurate. So let's take a look at what's coming out of this. The red curve here is the error rejection transfer function. And the key parameters for that are usually when it crosses over the -3 dB point, which according to this is about 57 hertz. And that makes sense. I expect a factor of 20 between the sample rate in a well-tuned system, between the sample rate and the 3 dB error rejection. So it's saying 57, that's pretty close. And another commonly quoted parameter for a control system like this is the crossover at 0 dB, which for us is about 89 hertz. And then the final one that's commonly quoted is the 3 dB control, which is 156 hertz. Okay, so that's the 3 dB there, and it's much further out. So you can see that there are 3 effective bandwidths that are specified or resulting from the simulation. And when you're designing your system for use with the beam control scaling law, this one, this 3 dB error rejection, is what we use there. So you can go through here and specify the sample rate of your camera or sensor. You can specify the latency, and this is usually how much time it takes to not only integrate, it's usually half the integration time, but also how long it takes to calculate a new command. And you can specify a gain here. You don't want to get too high with the gain, it'll go unstable, but yeah, 0.7 is a reasonable number there as well. So I'll do another high resolution calculation. There we go. So now we're getting 60-ish hertz. You can see I upped the gain. Now the bandwidth went up and the overshoot went up as well. Okay, so this tool is very nice for determining what these bandwidths, these 3 dB bandwidths are of the error rejection transfer function from engineering parameters. So those are 2 tools that we use to calculate requirements for adaptive optics and tilt control systems to compensate aberrations in the atmosphere. If you have any comments or questions, don't hesitate to contact us. Thank you very much for listening.